So connected to particles, now we are going to see the cases in friction when we have connected to particles. We saw connected particles, but we never consider these cases of friction. So now let us consider, because we are considering smooth surfaces. Now let us go back a little bit to them, and then we'll see examples when we have friction onto them. A mass of 150 grams is resting on a table. Resting on a table is connected to a mass of 200 grams hanging freely by a taut spring passing over a smooth pulley. The coefficient of friction between the table and the 150 kilogram mass is that if the system is released from rest, find particle acceleration of the system and the tension, then the distance there, as we are going to see. Now here so they are giving us our masses in grams. We first convert them to kilograms. So meaning, first of all now, how do you convert them to kilograms? We have 150 grams, it's going to be the same as 150 divided by 1,000, and this will be in kilograms. So this one is going to be 0.15 kilograms. And the time one of 200 grams, this is going to be 200 over 1,000 kilograms now, which will be 0.2 kilograms. Okay, so now we come and put our weights. So this is the particle, first of all, of mass 0. Now this one is on the table, 1.5 kilograms. Its weight now is going to be 0. The mass times the gravity. Of course, it's going to be having a reaction. Then it's connected by a taut spring. Taut means it's inextensible and you cannot. Then passing over the pulley, but now after it passes over this pulley, it has a mass of 200 grams, which is the same as 0.2 kilograms. Now, of course, it's going to be having a weight, it's going to exact, which is 0.2 times B. So that's the basic now. Of course, because the triple acceleration, of course, is going to be in this direction. So our acceleration is going to be in that direction there for this mass. Then for this one, it's going to be in that direction. Because the direction of accelerations helps us when we are dissolving. Okay, so because the table is not smooth, now you're going to expect some frictional force in that direction there. Okay, so now remember you're going to be having the tension in these two strings in that order. So T, then that is going to be also T. Okay, so part A, so I think we have finished the sketching. Then in part A, the thing has acceleration of the system. Now, remember, if the system is released from rest, so meaning our initial speed is going to be 0. So the particle is released from rest, so we need our acceleration, so meaning, of course, our initial velocity is going to be 0. So the question is, can we get our U? Do we have the distance? Do we have anything? The question is no. So now, acceleration of the particle, let us see. If I have this and it's going in this direction, it's going to be acted on by a certain mass. I also have this, but they are many. So now, to get the acceleration of the system in my part A, now, they are giving me mu. Okay, I also have my mu as third. So now, in that direction, so now I resolve in this direction on a 0.15 kg mass. Its acceleration here we base on the acceleration direction. So what is pulled in this direction is going to be our T. I think we see that our T is there. So our T in that direction, then we are going to have a force. Okay, our FR is equal to MA. That's what they are going to use. So our resultant force, the resultant force, you see what is pushing in that direction is going to be our T, then minus this force which is opposing F, will be equal to M, the mass which is 0.15, and the acceleration we don't know. Of course, we know that our friction is the same as mu r. So this F same as mu r. So putting it here, now I have my t minus mu r equaling 0.15a. But I know what mu r, I know what r is. From here, if we resolve vertical to the plane, my r is going to be equaling to just this. I'm going to be having on this particle, I'm going to be having my r equaling to 0.15 g. Why? Because we don't have any motion in upward direction. So my r here will be 0.15 times 98, our gravitational force. So 0.15 times 9.8, I get 1.47 newtons. So that's my resultant. So putting it there, remember I have this, I have also the resultant. So from there, my t minus r, then I have now also all this, which is 1.47 will be equal to 0.15a. So once I have that, it means when we simplify this, we shall get 0.9. So t, my t is going to be okay. The whole of this is giving us 0.49 equal to 0.15a, implying that now my t will be 0.15a then plus 0.49. I call this equation 1. So now I come to the 0.2 kilogram mole mass. You see it's in that direction. That's where our X is. So our resultant, it will be equal to mass times that direction. So the resultant, what is pushing it in this direction, is 0.2 g, then minus this 2 which is opposing, equaling to the mass, then times that. So remember the expression is going to be the same because the string is the same. Okay, so from here, we have our t already from there. So we have here 0.2 into 9.8, then minus our t. But remember I have my t here as 0.15a plus 0.49 equaling 0.2a. So after that, you see when I multiply there, I get 0.2 times 9.8, which is giving me 1.96, then minus 0.15a minus 0.49 equaling to 0.2a. When I take this side, I'll be having this minus this, so 1.96 minus 0.49 equaling 0.2a plus 0.15a. So here you get 1.47 equaling to, when I add there, this one is going to give me 0.358. From there, our solution is going to be getting 4.2 meters per second, and that's the answer there. So now we have our acceleration. Part B, they're asking us to get a tension in a string. So now part B, remember our tension from there, from 1, our tension in a string is going to be 0.15 into now 4.2 plus 0.49. This is 9. Our tension here is going to be 1.12 newtons. So we have tension there. So the distance moved by 105 grams in the first second of the motion, assuming that nothing impedes the masses. So if you want now to get the nth second, remember our formula for the nth, the distance covered in the nth second. So it's given by Sn minus Sn minus 1. So we are in the first second, this is the distance which is going to be covered. So our S in the first second is going to be S1 minus S into 1 minus 1, which will be S in the first second minus S in this. So in the 0 second, of course, the equation we are going to use using our S equaling to UT plus a half AT squared. So when you put them there, I think it can be my S in the first second is going to be S1. So I'm going to be having my initial, which is 0. Remember our U is 0 because the particle was from rest. Okay, so there I'm going to be having 0 into 1, then plus a half our acceleration, which is 4.2, then 1 squared minus, of course, when we put in here S of 0, okay, our S1 here is going to be, if we put in, so 0 into 1 plus a half into 4.2, 1 squared. Then our S of 0 is going to be 0 into 0 plus a half of 4.2 into 0, because here our time is 0. So which will give us a 0. So this will be a 0. So our distance in the first second is going to be half of that by the 2.1 meters. So therefore 2.1 meters are covered by 145 grams mass in the first second day. So that's it, members. I wish you well. Hope you can take this note. SN, because this is the distance covered in the nth second by a particle